Okay, continuing review from last class period. Chapter 8 talked about momentum, specifically linear momentum. Oh, Maxwell. They're doing it. He's a front row student. Sexual harassment right there.
Whoa.
Hey.
What just happened? What just happened? What? No!
Wow. No, he called you baby.
Oh!
That's racism.
What? Racism?
Dang!
Did I miss something?
Identifying as a woman? I can if I want to.
You don't know. That's the way to
No, I was kidding because she didn't take offense. But, in today's world.
Honestly.
Okay, so momentum, mass times velocity. It's a vector, points whatever the direction velocity points. Impulse is the term for when we apply Newton's second law. Newton's second law, the sum of the forces is change in momentum over change in time. And so if we multiply across, change in momentum is equal to, and I'm going to change from sum of the forces to net force. By now you know that means the same thing. And so this side here we call the impulse. And the other side is the change in momentum. So impulse equals change in momentum. What's special about impulse? Well, if you calculate net force multiplied by the time it acts, you can calculate how much momentum changes. And so we call that calculation of net force times how long it acts, the impulse. So when is momentum conserved? It doesn't have to be elastic.
Isn't momentum always conserved?
Not always. If I take this pin and let go, momentum is not conserved for that pin. It increases. Yeah, if the net force is zero, or if delta t is really small. So that's why we say collisions, the delta t is really small. So between the two colliding things, we conserve momentum during the collision, not before and after, but during. So the graphical analysis is if you have a force that you can draw like this, force on this axis, time on this axis, time. Then once again, just like when we did work, the area under this is the impulse. So that's what the graphical analysis is. That new form of Newton's second law, that's the actual form of Newton's second law. Newton's second law, and when we get to relativity next semester, how many people are going to be here next semester? Nice. Excellent. I love returning students. Almost as much as I just love all my students, Okay, I don't know. I said that wrong. You know what I mean. Just want to make sure it doesn't sound like, oh, he doesn't love the ones who are new or who aren't coming back. Okay, so staying with the topic here, as we'll learn in relativity next semester at the very, very end, Newton's second law, force net equals derivative of momentum with respect to time. That is correct under relativity. Some of the forces is MA. No, that fails. So it's an important form to know. Center of mass, we didn't really talk about center of mass except for to say that the center of mass is the part of an object that's like the average position of the mass. And of course, calculus, you did a lot with it.
Wait, we did a lot of what with calculus?
Calculating center of mass.
Oh, yes, we did.
But it's the average position of where the mass is. It's the place where it's going to balance. And when I take an object like this pin and I throw it at David, the center of mass follows the nice parabola that we learned about earlier, even though the rest of it is all flopping around. We talked about collisions in one dimension. We only did one-dimensional collisions. And we said that for the collisions, we're going to say momentum is conserved because the time for the collision is very short. but we still have two types of collisions: elastic collisions, which are collisions where kinetic energy is conserved, and inelastic collisions where it's not. And in our general physics terminology, we just say inelastic means they stick together. Because if you want to be all technical, every collision is going to be inelastic. No collision is going to perfectly conserve kinetic energy. But we're going to call the ones that stick together inelastic, in which case we have the simple relationship that V1 final equals V2 final, or the elastic with the much more complex kinetic energy initial equals kinetic energy final, which involves 1/2 mv squared. Equilibrium. Equilibrium means equal forces. And so things in equilibrium have a net force of 0. But that's only one of the two conditions of equilibrium. There's also rotational equilibrium. If the net torque is 0, then it's in rotational equilibrium, so you put the two together, net force equals 0 and net torque equals 0, and you have equilibrium. Now, just to make sure things are simple, if I'm standing here, what is the condition for me to be in a stable equilibrium?
Your center of mass has to be over your point of contact with the ground.
It has to be over the contact. So if I come a little bit to the side, I'll come back. But if I go a little too far, then I go out of equilibrium. I fall over, then I'm in an unstable situation. So stable equilibrium, you tip it a little, it'll come back. Unstable, were I able to balance this, you know in theory it could be balanced. But if I was able to, any small jostle and it falls, that's unstable. And neutral equilibrium is like this. I move it, it just finds a new equilibrium over there. Doesn't come back, but doesn't go flying away. So with torques, make sure you remember torque vector is equal to R vector cross F vector. What happens if you do F cross R?
That's cross product of the radius and the force exerted, isn't it?
Well, R cross F is torque, which is cross product of radius and force. But what would F cross R give you? I'll give you the answer because we're reviewing. You may not remember, right? That's how we go over it. It would reverse the direction. And so if you do F cross R, it's minus torque instead of plus torque. How do you find the direction with the cross product?
How do you find what?
The direction. If I have,
Isn't it the sum of the vectors?
if I have a force acting like this,
The right-hand rule.
and it's acting on an object like this, about this point, so my R vector is going like that. What direction is that torque? Right hand rule. Index finger in the direction of the first item, so index finger in the direction of R. Keep that index finger pointing that way and orient your hands. Your middle finger can point in the direction of F. Your thumb points into the board. And so that's the direction. By convention, we generally say out is positive and in is negative, so we'd say that that is a negative torque. So the right-hand rule. And remember, the magnitude of the torque is R perpendicular times F, or RF times sine theta. Now, what is theta in this equation, RF sine theta?
Isn't that the angle between the force and the rod or
The force and the radius. So in my picture here, that theta would be, I'll put it on this side. It doesn't matter which side you put it on because sine is symmetric about 90 degrees. So I could have put it on that side or I could have put it on this side. But it has to be between R and F. So if you have an angle and it's not the angle between R and F, then either find the angle between R and F or just go back and say, okay, what is the R perpendicular, and calculate it on your own. Rotational form of Newton's second law. What's the rotational equivalent for force? Torque. So it's going to be sum of the torques. What's the rotational equivalent for mass? Moment of inertia. And what's the rotational equivalent for acceleration? Easiest question of all. Angular acceleration. And so that's the rotational equivalent of Newton's second law. It tells you that a torque, which as you recall my dad called the amount of twist, it's a twisting force, the net torque is the moment of inertia times the angular acceleration. Larger moment of inertia, just like larger mass, it's not going to have as much acceleration for the same torque. Simple machines, what's the goal of a simple machine?
To make life easier.
To make life easier. Well, that's true. It's to do work with less force. But you don't get something for nothing. You have to put the same amount of work in, so you're going to have to put that smaller force in for a larger distance. But, sliding a car up a ramp is a whole lot easier than just lifting the car up onto a dock. And so that ramp is a simple machine that saves us a lot of work, or not a lot of work, but a lot of force. I've actually talked about, well, no, I haven't. Angular momentum has an equation of, there's two ways of writing it. This one is using the angular, another one is equal to R cross momentum, R cross linear momentum. So two different ways you can write the angular momentum depending on how you're dealing with a situation. The second one we would usually use with a point mass, which you know what we did in this class? No angular momentum problems with a point mass. Rotational inertia, the general form, I is equal to sum over all of the pieces, mass of the piece times radius of that piece. Radius means the distance from the axis of rotation, perpendicular to the axis, squared. And in a problem, we usually give you a couple pieces and you use that equation. So if I have two masses going around a circle, then you say, okay, for each mass, my I is this mass times its radius about the axis of rotation squared. And then I add them up. Or we give you a solid shape and you look in the table. So like a solid cylinder, you look in the table, it says 1/2 mr squared, and you calculate based on the table. Then we have rotational and kinematic equations, as I actually introduced in class on Wednesday. They're all the same as the linear ones, except for you change from the linear variable to the rotational. So if you could do them with linear, you can do them with rotational, because as it goes, the song remains the same. Work done by torque, I'm just going to write this. It's torque times the angle it goes through. Remember, work done by force was force dot delta x, where the dot meant we were multiplying the parallel parts. If we go back a slide, we had torque is R cross F, distance crossed with force. What does the cross mean?
Perpendicular.
Multiply the perpendicular parts. And a cross product gives you a vector, so torque is a vector, whereas a dot product gave you a scalar, so work is a scalar. Remember the units here, newtons times meters, we call that a newton meter or a joule. Whereas the unit here, meters times newtons, we just call them meters times newtons. We do not call that joules. So never say joules for the unit of torque. Okay, now we get into the stuff that most people feel a lot better about. Common states of matter. You should know that a solid, the atoms are in fixed positions with small vibrations. In a liquid, the atoms can move past each other, but they can't leave the group of atoms. And in a gas, they can move freely. Temperature is a measurement proportional to the average energy of the molecules. So at low temperature, the molecules don't have much energy. It's easy for them to be held in one place in a solid. That's why solids are low temperature. Of course, this table's solid. Is it low temperature? Well, if you heat it up enough, yes, you can make it change state, although you'll probably go straight to a gas state, right? You're not going to make a liquid table. If it's made out of wood. It's made out of polymer. Yeah, you probably will make it a liquid. Okay, so you heat it up, and when you get up to, well, as you put in heat, what is the definition of heat?
Energy.
It's energy being transferred without doing work. So it's caused by it's caused by molecules bouncing off of each other and transferring energy that way rather than having like a plunger push on something. So you put heat into something, the energy increases. Normally, as you put heat in, the energy increases, the temperature goes up. So we have the relationship Q equals mc delta T for how the temperature changes as you put in heat. But when you get to the temperature where the molecules, you add a little more energy and have enough energy to break free, then the temperature stays the same and the energy just goes into changing the phase, changing it from, in this case, a solid to a liquid. And then we had Q equals mass times the mass that's converted, the mass that melts in this case, times the latent heat. Now these are in later chapters, but because I'm talking about them here, I wanted to make sure we talked about what the difference is between the phases and why it changes from one to another. So to go, then if we have a liquid and we put in heat, what should happen? Before it goes to gas.
Oh, it should boil.
It heats up, right? The temperature rises as you put in heat. And so we know heats up means temperature rises, even though heat is not temperature, heat causes a change in temperature. But then when we get to the boiling point, which is the point where the vapor pressure of the liquid is equal to the atmospheric pressure, which means that little droplets in the fluid are going to, because they have an equal or higher pressure than atmospheric pressure, they're going to expand instead of being compressed, and then they float up. That's what boiling is. When we get to that point, we put in more heat, the molecules break free of the liquid instead of the temperature going up. And so it's constant temperature and phase changes. Pressure, we had a number of units here. Pascals, 101325, I think. Pascals is the average atmospheric pressure, what we call 1 atmosphere. PSI, it's like 14.7 pounds per square inch. That's what PSI is 1 atmosphere. Torr, named after Torricelli, is millimeters of mercury. Because if you put a vacuum on the top of the column of mercury and atmospheric pressure at the bottom, the height of the column is going to be 760 millimeters. And pressure difference is calculated as change in pressure is equal to the density of my fluid times G times the height or depth. So that's how we can go from, for instance, torr to an atmosphere using the density of mercury, because we usually use mercury for our barometers. But you could use water as well. So like in chemistry lab, you might use water in a manometer. You might remember the homework problem with the manometer where you have something like this. And if you have water level here and here, which side is higher pressure? The left side is higher pressure because it pushed down. So the pressure here is the same, and then you're going to lower pressure as you go up because pressure is caused by the weight of material above you. Gauge pressure is pressure relative to a reference point. Absolute pressure is, well, just like it says, it's the actual force per unit area. Pressure is force per unit area. It's the same in all directions. And what's the minimum pressure you can possibly have?
No pressure.
It's zero, no pressure.
That's a vacuum.
And so we call that a vacuum. Gauge pressure relative to a gauge, usually that gauge is atmospheric pressure. So in my automobile tire, I have a gauge pressure of 32 psi. What that means is it's 32 pounds per square inch above atmospheric pressure. So if atmospheric pressure here is 14.7 pounds per square inch, what's the absolute pressure inside my car tire? It's 14.7 plus 32. So it's easy to switch back and forth, but you have to be aware of those. Now, if you are using the ideal gas law, which one should you use? Gauge, absolute, or does it matter?
Use absolute.
Must use absolute if you're using something that is the pressure. Gauge pressure is great for changing pressure, and of course we use it for things like, well, what's pressure in our tire? But if you're using the ideal gas law, you have to use absolute pressure. Pascal's principle says the pressure, well, the technical terminology is if you put a pressure on a constrained fluid, that pressure is distributed the same everywhere. So if I raise the pressure of the fluid by 10 psi here, everywhere else the pressure also goes up by 10 psi. And we can use this to make simple machines such as the hydraulic lift we talked about. Archimedes' principle we did a cool lab on. Archimedes' principle said that the weight of the displaced fluid is equal to the buoyant force. Buoyant force is the net force acting on object due to the pressure in the fluid. Surface tension, I forgot to cross that out. We won't have surface tension on the test. Continuing with fluids, we didn't talk about turbulent flow, but we did talk about laminar flow. Laminar means in layers. So smooth flow is laminar flow. It's the only kind we talked about. We talked about the flow rate Q, for now Q was heat, now it's flow rate. Q is equal to the speed times the area. I did mention there's also a mass flow rate, which is just multiply that by density. Still use the same Q variable, I think. But we only did the volumetric flow rate, which is speed times area. If I have a continuous flowing fluid, my flow rate should remain constant. So VA is equal to VA. If A increases, what happens to V? If VA is constant and A increases, what happens to V?
It increases as well.
It's going to have to decrease because VA stays constant. And so if V decreases, what happens to the pressure?
If the volume decreases.
No, the speed, the flow. Yeah, I have to be careful.
Yeah.
If the speed V decreases, then what happens to the pressure in the fluid?
Yeah.
It's going to increase because of the Bernoulli relation. Bernoulli relation says the faster the fluid's flowing, the lower the pressure drops. And so we had an equation for that. That's the Bernoulli equation. So you can relate any two places with the pressure, the speed of the fluid, and the elevation. And we didn't talk about viscosity, although we did have a nice catch-up, I think, example for viscosity that depends on the conditions. Or we didn't talk about osmosis. Now back to thermodynamics, back to Q being heat. I said it before, it was before we got to it officially. Temperature scales. One of the big problems that people had in the last test was simply with units. People tried to use Celsius or Fahrenheit with the ideal gas law. With the ideal gas law, you have to use an absolute pressure, or excuse me, temperature, you get pressure too, but you have to use an absolute temperature, which means kelvins for us, because it's the only one we know.
Not Celsius?
Right, not Celsius, because it's not absolute. It's not absolute, 0 is 0.
Oh, right.
That's what defines the absolute temperature scale. So, and of course, you need to be able to convert between them. It's not hard to convert between, it's just you have to know to do it. Also, another problem people had was they tried to use the ideal gas law with non-SI units using the SI value for R. That is, the value for R I gave you had joules, moles, and kelvins. And that gave you pressure in atmospheres and volume in liters. You have to convert your units so that all of your units work together. That was, I mean, it's sad I don't like taking off points. I didn't actually think of that as a problem when I made the question, but it turned out to be. Thermal expansion. For most materials, you put in heat, the temperature rises, and what happens to the volume? It expands. Maxwell. If I have a hole in a piece of metal, and I heat up that metal, what happens to the hole?
So the hole gets bigger and the ball gets bigger.
Yes, that's right. So we had two equations for thermal expansion, one that was linear, one that was volumetric. Delta L is equal to L0 alpha delta T, or delta V is equal to V0 beta delta T, where beta is approximately equal to 3 alpha. And in class, I actually talked about the geometry, I think. Either that or it was when I was talking to David. I did it at some point. Molar and atomic mass, just to make sure we have that squared away. The mass per mole is the mass for 6.022 times 10 to the 23rd molecules. The mass per molecule, of course, is per 1. So the difference in the two is that 6.022 times 10 to the 23rd, more commonly known as Avogadro's number. You have to know which one's which because we had the kinetic theory of gases where we had the equation that said VRMS, square root of, what was it, 3kT over m, or 3RT over capital M. The R is per mole, and so you have to use the molar mass. The K is per molecule, so you have to use the molecular mass. And once again, that was, it's not important things, but it was things that trip people up. Ideal gas. What makes a gas ideal? Has no volume.
And it's completely elastic.
And they don't interact at all unless they collide, in which case you have completely elastic collisions, no energy lost. Neither of these are actually true. So nothing's truly an ideal gas. There was a nice scrapbook last time where somebody had a meme on that. I know you guys don't get to see all the scrapbooks. I do, and it's kind of fun. And by the way, those of you who've already turned in your scrapbooks, I've already graded them even.
Oh, cool. So mine can be graded later today?
If it's turned in
No,
earlier.
literally turned it in like 10 minutes ago.
Yeah, probably. I just want people to know before the test exactly where they stand as early as possible. He's working on grading them today.
The lab.
Yeah. Okay, so back to this. We have those as ideal behaviors. How do we approximate ideal? How do we judge to say, oh, air is ideal? What do we use to make that approximation? We have two criteria, one for the volume, one for the collisions. By the way, I know in my review for the last exam, when I said phase diagram, I wrote the wrong diagram. I was very embarrassed about that afterward, but it's too late. Just thinking about reviewing and making mistakes.
Repeat the question.
What two conditions can we identify that will make a gas behave as if it's ideal? What condition would make it behave as if the molecules have no volume? Answer, if the space between the molecules is much, much bigger than the size of the molecules. And so if you have a low density for your gas, then it's going to behave fairly ideally as far as that criterion goes. The other one, the no energy lost during collisions. For that, if we have a high temperature, that means the molecules are hitting each other really hard. And so the percentage energy they lose per collision is going to be small. And so we can ignore it and say that it's pretty much elastic collisions because the percentage lost each time might be 0.0001%. Who's going to care?
So pretty much we want it to be a big area with a really high temperature.
We want it to be a low density, which means for the same number of molecules, a bigger volume,
right,
and a high temperature.
Okay.
So, I mean, to me, it's kind of important to know when we could use this and when we need to go to something that's more accurate, like the Van der Waals equation instead of the ideal gas law. Okay, Charles' law, Boyle's law, Gay-Lussac's law, Avogadro's law. You don't need to know any of those laws. Those were leading up to, you combine them all together and you get the ideal gas law. We've already talked about the temperature kinetic energy relationship. That is called the kinetic theory of gases, we have the kinetic energy is equal to, F times 1/2 kT, where F is the number of degrees of freedom. And the degrees of freedom, if it's an ideal gas, you have 3 degrees of freedom per molecule, so it's the number of molecules times 3. So we generally will say use F for the per molecule, and then you have 1/2 nRT, or 1/2 capital N KT in that relationship. We call that the equipartition theorem, that the amount of energy in each degree of freedom is the same, that 1/2 KT. And we were able to work that out for an ideal gas. Maxwell-Boltzmann distribution is a distribution of speeds that you have in an ideal gas at a given temperature. And one student here, David, did some calculations and was able to, in class, find the equation for the RMS speed and the average speed and the most probable speed based on that Maxwell-Boltzmann distribution. For the rest of you, not a big deal. Humidity. What is relative humidity? Notice I said relative humidity. What is it? Okay, it's how much moisture content you have in the air divided by the saturation level. So 100% relative humidity means that the air has as much water as it can hold. If you go above that, it has more water than it can hold. It is possible to make what we call a supersaturated atmosphere, where it has actually more water than it can hold. But any small disturbance is going to cause it to then condense, form water droplets. And so clouds form when you have humidity of 100%. Then it can't hold any more water. Water droplets then can condense into, water condenses into droplets, and that's what the fog is. You're seeing the water droplets. You're seeing the mist scattering off the water droplets, but that's for next semester. So how does temperature relate to the relative humidity? I mean, the easy answer is I don't think it does, but it's wrong.
Doesn't the temperature doesn't the increase in temperature help with evaporation? So
it does, yes. Remember, we talked about why do I have to turn on my AC to defrost?
When evaporation kind of happens, doesn't it also kind of lower the humidity in the air, making it so, never mind. Because evaporation.
When water evaporates, you're putting more moisture into it, raising it. But temperature, the higher the temperature, the more moisture the air can hold. And it's not a linear relation. If you double the temperature, you're going to hold a lot more than double the moisture in the air. And so as the temperature rises, if you keep the same amount of moisture in the air, the numerator stays the same, the denominator gets much bigger because you can hold a lot more, so the relative humidity drops as the temperature rises. So if you look at, in the morning, if you look at the relative humidity, it might say it's 95% relative humidity. You're like, oh, it's going to be a muggy one. And then if the temperature rises by 30 degrees, that relative humidity drops down to like 50%. And of course, this is the middle of summer, 50% at 96 degrees is still really uncomfortable, I think. But the humidity drops. So, weather people, I went to a weather conference a few years ago, and they're like, yeah, relative humidity is for the dorks. What they really should be talking about is the dew point. The dew point is the temperature where you would have 100% humidity with the current moisture content. And so the dew point doesn't matter what the temperature is. The dew point is 65 degrees. That's a fair amount of moisture in the air. If the dew point is 10 degrees, when I say degrees, I mean Fahrenheit now. That's a much lower amount of moisture in the air. Evaporation, boiling, we've already talked enough about those.
What was the, do we have to know, relative humidity, the moisture content over the percent?
You have to know that the relative humidity is the amount of moisture in the air divided by the saturation level. But you're not going to do an actual calculation with it. You need to know that. And you need to know that the moisture content the air can hold, the saturation level, changes dramatically with temperature, so higher temperature can hold much more moisture. Okay, heat and heat transfer mechanisms, whatever. Remember we had 2 units for heat. What's the one that we use almost every time in this class this year?
Joules or kilojoules?
We use joules almost every time. If we were in a European country and we went on a diet, we would measure our energy intake in joules. But we're not. We're in the United States of America, where we still use
Calories.
the alternative of the calorie. And the conversion, 1 calorie equals 4.186 joules. My son's in general chemistry, is doing some general chemistry homework last night, and they have 4.184. I don't understand. I don't. And of course, I hope I remember which one's which. The calorie is defined by 1 calorie is the amount of heat to raise 1 gram of pure water from 14.5 Celsius to 15.5 Celsius. That's the definition of a calorie. It is something that can be reproduced anywhere in the world, right? Find pure water, well, at standard pressure. I should add that. So that's the definition of a calorie. Something we never once talked about is the British thermal unit. The British thermal unit is the amount of heat necessary to raise, I think it's 1 pound of water by 1 degree Fahrenheit, something like that. And so it's also reproducible, but it's based on imperial units. At least the calorie is based on SI units, right? I mean, it's not the worst thing we could have. So we talked about the specific heat capacity. Q is equal to MC delta T. Which thing in there is the specific heat capacity? The C. What makes the C specific and not just the heat capacity?
Because it's specific to the object that's being measured, isn't it?
Actually, it's specific to the material.
Like,
That's what the specific is. If you use a lowercase, it's specific to the material. And so if you have aluminum, it's the same specific heat capacity. Heat capacity with a capital C is for a specific object. So if I have a block of aluminum that's bigger, it has a bigger heat capacity. If it's small, it has a small heat capacity. We never use that because it's just a lot easier to talk about per unit mass. So we had that calorimetry thing. What was the key to solving calorimetry problems?
equilibrium.
You reach equilibrium and
Some of it was like
the sum of the heats is 0, which I think is what also Max was saying. So you have an insulated system. You put 2 things that are different temperatures together. Second law of thermodynamics says that heat will spontaneously flow from the hot one to the cold one. And so the net heat flow, since it's going from one to the other, is 0. So you just calculate the heat for each one, add them up, equals 0. It is important to get your signs correct. I don't know what you guys learned in your specific general chemistry classes, but some classes will say heat gained equals heat lost. And so you have 2 different equations. The heat gained is going to be MC temperature final minus temperature initial. The heat lost is MC temperature initial minus temperature final. I don't know why you'd want to have those 2 separate equations and have to worry about which one's which. So I just say Q equals MC temperature final minus temperature initial, add them up, equals 0. Remember phase transitions, we had Q is equal to the mass times the latent heat. In this case, mass is how much mass was melted or frozen or vaporized. The latent heat is specific to the type of material and the phase transition. So water freezing is a different latent heat than water boiling. Phase diagrams. Pressure, temperature, how's that? Better, right? Mechanisms for heat, conduction. Andy will tell you conduction means that you have contact. And then you have convection. Okay, I know Andy has things for all of these. So convection is when you have an intermediary. So for instance, in the oceans, we have streams that flow from the pole around South America, back up into the Atlantic, back around South America, and back up to the pole. They're big convection loops. And it's kind of weird because you're like, how do they cross over each other? One's higher and one's lower because of temperature difference. You know, it's cold when it leaves the pole, warm when it's coming back, and that makes them so they go at different levels because the density is different at different temperatures. By the way, water is unique. What are some of the unique properties of water?
Water is more dense. It's solid.
It's less dense when
Less
it's
dense than
solid.
solid.
Less dense when it's solid. It expands when it freezes instead of contracting because of its hydrogen bonds. Water also, because of the hydrogen bonds, has a high specific heat. That means that you put a bunch of heat in, the temperature doesn't change much compared to most things, which helps to buffer the temperature. So temperature fluctuations near bodied water are much smaller than they would be far from bodied water with all other conditions the same. Okay, radiation. Radiation is electromagnetic waves. What's your sign for that, Andy? For radiation. Yeah.
Oh, radiation. This is
Okay.
just this.
Just this.
This.
So which one of these do we use when we have a forced air system in our house? Convection. Which one of these is in play when you walk out on a sunny day?
Radiation.
Radiation. Actually, I probably would have been better to say when you have a sunroom in your house, it's 30 degrees out, and you sit in the sunroom and you're baking. Radiation quick. Stefan Boltzmann law and Wien's law, we didn't talk about this at all. And with the Stefan Boltzmann, all we had was the power for radiation is sigma epsilon A that's the power for heating through radiation, where T environment is the temperature of the environment that's radiating. T object is the temperature of object that's absorbing or emitting. Sigma is a constant, Stefan Boltzmann constant. Epsilon is the emissivity. Things that are silvered have an emissivity very close to zero. That means they're very bad at absorbing radiation and very bad at emitting radiation. Things that are black have an emissivity very close to 1 because they're very close to a perfect absorber, very close to a perfect emitter. So we tend to call this black body radiation because black does it better. Conduction has also equation power is equal to K cross-sectional area divided by length multiplied by the temperature difference. You might remember that coming into play on the last exam. Thermodynamics. Thermodynamics, we have the 4 laws of thermodynamics. In order, what is the one we talk about first in the 4 laws?
Zero.
The 0th law, right? I didn't want to get away with saying what's the 0th. So what is the 0th law?
It's temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C.
That's exactly right. And it seems so obvious, but then when you get to the actual definition of temperature that has to do with the derivative of entropy, you're like, whoa, it didn't have to be true. But it is. Then we get to the first law. The first law, energy cannot be created or destroyed. And the way we usually write that is the change in internal energy is equal to the heat added minus the work done by the system. Second law, many different statements. And on the last test, you had to say which ones were statements of the second law. So one statement of the second law, heat spontaneously flows from hotter object to a colder object. Another statement of the second law says that it's impossible to make a heat engine that converts all of the heat into work. You're always going to have some exhausted. A third statement is that every natural process is going to, no natural process can decrease the entropy of the universe. Now you can have a natural process that decreases the entropy of an object. For instance, if I have water in a cup and I put it in the freezer, the water in the cup freezes. The entropy dropped. By even the general chemistry terminology of the amount of disorder went down. So the entropy in that ice cube dropped. That's not violating the second law of thermodynamics because you drew heat out of there and then you exhausted it outside. And a refrigerator always exhausts more heat at high temperature than it takes out at low temperature. And so as a result, the net result is an increase in the entropy of the universe, even though you decrease the entropy of that ice.
Entropy is continually, or
And entropy is constantly increasing, basically. And as we learned in this class, entropy is a measurement of how probable something is. And so things are constantly going to more probable states rather than improbable states. Unless, of course, you're into Hitchhiker's Guide to the Galaxy and you have an improbability drive. Then you might be reversing that. But you know what? That's nice. Heat engines. What's the purpose of a heat engine?
To convert.
Convert heat into usable energy to work. And according to the second law, you can't make one that just completely converts heat to work. You're always going to have some exhausted heat. And so we have those diagrams that show heat coming in, Q at high temperature. Here's my heat engine. Heat going out, Q at cold temperature. And then you have the mechanical work coming out. And for a complete cycle, the change in internal energy for the heat engine has to be zero, otherwise it would freeze or melt. And so you have, it turns out that what goes in, QH, is equal to what goes out, work plus Q cold. The efficiency is what you wanted out. What do you want out of a heat engine? Work. Divided by what you put in. What did you put into the heat engine? Q at high temperature. So that's the definition of efficiency for a heat engine. Then we have the Carnot engine. Carnot engine is not real. It's not achievable. You can't make one. But the Carnot cycle with the isothermal, then adiabatic, then isothermal, then adiabatic, can be shown to be the best possible efficiency that can be produced. And for the Carnot cycle, the efficiency ideal turns out to be 1 minus temperature cold over temperature hot. And so that Carnot gives us the ideal efficiency. It tells us what we can aim for. So on our last test, you had a problem where you were to find what percentage of ideal efficiency you produced. That is, you were supposed to take these two and divide them to find what percentage of ideal you actually had. Okay, we did not talk about the heat pumps, and we didn't really talk about entropy. We have 2 minutes to talk about the last material, about oscillations and sound. So simple harmonic motion is going to follow Hooke's law. That is, you have a required relationship that you have. Boy, I'm going to move over. The net force vector is equal to minus K delta X. It's linear and restoring. Linear because the force is proportional to how much you have moved away from equilibrium. Restoring because of that minus sign, so the direction of the force is in the opposite direction of the displacement. That is absolutely required for oscillatory motion. You might wonder why we put so much emphasis on simple harmonic oscillation and not on anything else. Because in nature, even if you talk about something like the bonds between atoms and the vibrations that occur because of those bonds are not springs. But if you go to organic class, she's going to bring out a spring holding two balls together as an example, because if the oscillations are small, which they are for molecules, then you can linearize the force. And if you linearize the force, it becomes a simple harmonic oscillator. And so in nature, almost every force can be treated like this. You have simple harmonic oscillations. Make sure you know those terms: period, frequency, simple pendulum. What's a condition for a simple pendulum to be a simple harmonic oscillator? Small amplitude. So sine theta is approximately equal to theta in radians. Don't try to apply that in degrees, in radians. And for a simple harmonic oscillator, omega is square root k over m. For a simple pendulum, that turns out to be square root of g over L. Damped oscillations, that only applies to David. Remember the difference in transverse and longitudinal waves, and then standing waves and musical things. So we didn't talk about the audible range, but we did talk about intensity level in decibels. We talked about resonance in pipes, timbre, pitch, and beats. So pitch, frequency, you double the frequency. How big of a musical step have you taken? Go ahead, Nancy.
About the scrapbook, sorry.
Oh, okay.
Do you,
There you go, 452.
what are like the exact requirements? You need a table of contents and then all 25.
Okay, so the exact requirements are you need the last 5, and they can be anything from chapter 1 through 17 that's not a repeat. But for my evaluation for extra credit, you need to have a table of contents, and I'm going to be looking at, how interesting the entries were, how pretty it is, how easy to navigate it is. Yeah, so there was our fuzzy judgments there.
So the table of contents is just kind of extra credit stuff?
It's for aiming for the extra credit, yeah.
Transitions? Extra credit too?
No. All right, have a great Sabbath. Remember the Sabbath day to keep it holy. Don't be studying on the Sabbath day.